just check the speaker. Yep. I think I can hear you guys now. All right, let's go to OneNote. Announcement. Sorry about any kind of delay for the grading the lab report. It's gonna take another day or up to the weekend. So I'm just trying to figure out how I just organize all the values and answers to within a reasonable range. So it's gonna take a little bit more time than I expected. So please just hang in there. I'm pretty much trying to be generous on the lab report at least, not like the quiz or exam. And another thing, the homeworks, the solution is gonna be posted by Wednesday and before the lab this Thursday, which we don't have any labs this week. It's gonna be the lecture for the biflow dimensional analysis. So you can just focus on the lab 2. If you haven't submitted the lab 1 report, please do so. You still can get at least 50% of the lab scores. So I'm pretty much encourage you to do it even after the due date. And what else? Yeah, exams next week. I'm gonna just talk about more exam materials tomorrow. So it's pretty much same format, but I'm gonna have a 15 minutes exam. So you might have some more problems, in addition to some multi-choice problem like that in the quiz. So I'm gonna just talk about it. It's gonna cover chapter 6 and 7, by the way, not the chapters 8. So let's get in more details of the exam tomorrow. All right, let's get into the lecture. So yesterday we finished up the subchapter 7.5, which just we can find the pi terms by inspection. So basically, just as long as you follow the 3 rules, then you can just find the combination of the variables to make all the units 0, which means dimensionless. So basically, you can just find several pi terms, a pair of, or the combination of pi terms, of course. Then what you can do is, if you know any kind of looks similar to the common dimensionless group, then you can just take the whatever operator you want to manipulate tweak the shape and the form of the pi terms to make things really good, like a Reynolds number. All right. So here's the list of the common dimensionless groups. You can go to textbook page 278. If you have a little bit different textbook version, you might just find that subchapter, common dimensionless groups in fluid mechanics. Then you will have the list of the kind of dimensionless coefficient. So the most famous number is the Reynolds number. Of course, we know it's the ratio of the inertia force divided by the viscous force. Then you can already know if the Reynolds number is far less than 1. This we call the creeping flows. Sometimes the Stokes flow. In that case, the viscous flow, of course, you can see the ratio here. Viscous flow dominates the flow fields. Therefore, we don't have to consider any inertia force. The advantage of the Stokes flow is we can just eliminate the whole convective acceleration in the Navier-Stokes equation. So the whole equation pretty much simplified into the just a pure viscous flow field. All right, if the Reynolds number is larger than a certain number, I didn't say any kind of specific number here. If it's a biflow, it's going to be like 4,000. If it's the open end, the horizontal plate, it's going to be 20,000, the 50,000 Reynolds number. That means you will see any types of turbulence, vortices, eddy currents in the flow. So I just make an open number, for example, 4,000 for the circular pipe flow. You'll see the turbulence. Oops. Yeah, so that's what the Reynolds number indicates in the flow field. So if you see like a higher Reynolds number, that indicates you will see any types of like a turbulence flow, which is also including the flow separation, which has usually occurred in the transient flow, which is between the laminar flow and turbulent flow. That's pretty much the indicator that you can see in the specific, like a certain condition of the flow. So it depends on the dimensions and geometry of the flow. So, but still, this is the most important Reynolds number whenever you see the flow. So there's another one, is a fluid number that's related to, you can see the G here, which is gravitational acceleration. So basically, it's not just about the flows moves vertically up and down. No. If you think it's a ship, we have a tugboat or any boat that's flowing in the open water, then of course, if any disturbance by a tugboat or like you throw stones in the water, then you will see some wave, right? Something like that. Then the wave is actually closely related to the gravitational acceleration, because once you have the maximum heights of the wave like this, that's going to be, just settle down to the sea level here. Then because of the inertia force, it's going to go down deeper in the sea. Then it's just trying to get it back to the sea level. So this is pretty much related to the gravitational acceleration. And thing is, if the boat, the L is characteristic length here, let's say just for example, we have a wave like that. The ship is positions like this. Then sometimes ship is large enough to cover the one cycle of the wave, things like that. Then you will see the wave can kind of block the speed of the boat. Sometimes if you just design the boat large enough to cover, overcome all the waves propagation and effects within the surface, then it's gonna just have a maximum speed. So that's pretty much the relate to the fluid number here. So you can just think about those kind of wave effects in the water. But that's usually happens in the free surface. So whenever you have an interface of the fluid, which is air in the water, or like a free surface means there's a gas in the liquid. So gases usually we don't consider any kind of viscosity relative to the liquid. So that's the one of the case we always consider the fluid number. There's an oil number. You already have this oil number in the previous lecture. Then this is the pressure force divided by the inertia force. And if it's 0, let me just see. I don't have that much space. If it's 0, it's we call the inviscid flow, the frictionless flow. It's the same meaning. Flow. And if you're interested in, I'm gonna just talk about this number again in the next slide. But if you're interested in the pressure drop within the pipe, or pressure drop between the inlet and outlet of the pump, or connections or fittings, then this can be converted into the delta P over rho V squared. And this is what you can called like a cavitation number. Is a vapor pressure divided by the rho v square. That means if you experience any kind of flow get accelerated within the two ends, like inlet and outlet, then if it's too fast, there's going to be the pressure drop significantly within the fitting or the device. Then you will see the vapors which is resolved into the liquid in the waters, for example, just popping up as a bubble. Then that can be, oops, sorry about that. That can be explained by this Euler number, which is now we call the cavitation number. Then the Cauchy number, Mach number, we call it. The Mach number is just simply divided by the velocity divided by the speed of sound. That's basically inertial force divided by the compressibility force. The compressibility force is another name, has like elastic force. So if the speed of fluid is high enough, we usually say like a larger than 0.3 Mach number, then we have to consider the compressible effects of by the speed within the fluid, something like air. When you just hit the Mach number by like a aircraft, then it's gonna just have a really huge sound, and all the behavior of the fluid field, it's actually really different from the one we think about the laminar flow and the turbulent flow less than 0.3 Mach number. Stroh number is relating to the oscillation, unsteady flow. The omega is pretty much the frequency of the oscillation. Then we're gonna just talk about this number later when you just do the lab for the circular cylinder within the flow field. Then it's gonna make the oscillation and eddy currents beyond the flow. So you can just consider what's the Stroh number. It's something like you'll see sometimes eddies looks like that. All right, if you have some object within the flow. The Weber number is all about the surface tension. So the surface tension, you can just think about the droplet. If you just have a droplet on the surface, how much angles does it have between the surface and the drumlet? If it has a higher surface tension, it's going to have like a more aggressive angle between the surface. And another way to think about the Weber number, the surface tension, is when you just spray the disinfectant, then you want to control the size of the spray. Then you want to control the diameter of the spray. Then the drumlet actually forms the area of the spreading area it depends on the inertial force, which is the velocity of the spray. So if you just decrease the velocity of the spray, then it just narrows down to like a small circle area. Then if you just increase the inertial force, it's going to spread out more, right? Then those behavior of the flow can be explained by the Weber number. And the other things like a velocity ratio is obvious, relative roughness. So the surface of roughness really plays a big role when you think about the frictional force, frictional flow, viscous flow in the pipe. So we have to consider, I don't know what happened to my tablet here. Okay, looks good. Yeah. So whenever you have a viscous flow, the roughness is really the important thing. And that is divided by the characteristic length. For example, if it's a pipe flow, the diameter of the inner diameter of the pipe is the one, can be the reference length for the roughness. That's why we have this ratio. Length, yep, angle of attack, loss coefficient, zone. You might want to see the drag coefficient, CD. We already deal with this drag coefficient, which is expressed here, d over 1 over 2 rho v square L square. So L square here is basically the reference area. For example, the smooth sphere that we are dealing with in the lab 2, we use the frontal area, just the cross-sectional area of the sphere, the pi r square, or pi d square over 4, which I had to make a typo in the lab handout. Oh, hold on, please. What happened with my? Okay, that's good. Then we have a lift coefficient that's pretty much, closely related to the drag coefficient. But when you consider the airfoil, we also consider the lift force by the flow. That's the pretty much perpendicular to the drag coefficient. So those are the list of the dimensionless group. Whenever you consider the flow field and the flow behaviors, and you just include all the variables which may be important for the flow behavior, then those are gonna form the dimensionless group such like that. So for example, a Reynolds number came up every single example problems, then we solve for the problem in the chapter 7. So that's why we always have a Reynolds number. So whenever you have a similar type, some similar format of the pi term, then you want to convert into the Reynolds number. Then this is the easiest one you can control in the flow field, especially in the lab. So that's going to be usually positioned in the x-axis when you design the experiments. All right, modeling and similitude. So we now talk about the model a lot. So it's basically the similar physical system that can be used in the lab to predict the behavior of the flow field. So for example, like we have aircraft, we don't want to just fly over in the air to measure all the flow field velocity and pressure differences and shear stress, things like that on the airfoil. No, you gotta just make the part of it and put it into the lab and downscale it and just run the experiments, right? That's what you call a model. Because we need lower cost and we can just fabricate more easily, and within like a day or two, if it's simple enough, we can just run the experiments to get the relationship between the pi terms. Then we can scale it up to the real device or the system. So we gonna talk about the relationship between the prototype and the model. The prototype is pretty much the actual system and device. So you want to build a real system to test its performance and all the behaviors within the actual flow field. But then before building the prototype, we want to test with the model. Then throughout the dimensional analysis, we know we can have the relationship between the pi terms. So we don't have to control all single variables that plays a really important role in the flow field. So we just focus on the pi terms now. When you have a very similar system, or let's say just identical system in a scaled model, just downsize the whole things in the small scale, and then we can just use the same relationship between the pi terms. Let's say we have n pi terms, 1, 2, 3, 4 to n. Then for the model, we just make it as close as possible in the smaller scale. Then you can just apply the same function for the pi terms. All right. Then can you just have a scale down to 1 over half, 1 over 2? Then can you just have the velocity all the 1 over half and the pressure drop is just 1 over 2? No, that's not works like that. We have to consider the pi term, not each variable. So a model design condition means sometimes we call the similarity requirements. all the pi terms, each pi term has to be same because those pi terms are dimensionless. Therefore, even if we scale down the system, this pi term has to be same for the model, all the pi term. Then there's three types of similarity we can consider within the pi terms. The first one is a geometric similarity. Of course, we are scaling the model from the prototype or the actual system. So if I just reduce the size of the system like a pipe, the diameter is one half of the prototype, then we have a scale is 0.5 and 1. There's 1/2, something like that. So that's a scale, geometric scale. Then dynamic similarity is all about the forces. So when you just have a force within the relationship between the model and the prototype, for example, like inertia force and the viscous force or the gravitational acceleration. So the ratio of the force in the model and the prototype has to be same to make whole things the similar, all right? And finally, there's a kinematic similarity that is basically within the flow field, the streamline pattern has to be the same in the prototype. So the ratio of the velocity should be constant, ratio of the acceleration should be constant. So then when you just have all the pi terms have the same number, same values that has in the model, then we can predict the behavior, flow behavior for the prototype. So here, I just write down the pi1 equals same as a pi1m, which is model. That's basically, we just took the dependent pi term. So whenever you have a pi term in front here, usually we have a variable of interest placed in this first pi term. For example, like a pressure drop per unit length was in the first pi term. Then the rest of them was like a Reynolds number or something other. Surface roughness, we're gonna just talk about it later. But if there's like a 3 pi terms, the first one includes the dependent variable. So let's take a look at one of the example problem we have seen it before. When you consider the plate here, then just trying to find the drag force based on the variables given in the problem. We have a width given, height was given, and the properties of the fluid was given, rho and mu, and the velocity is one of the variables. Then we're trying to find the drag force. And of course, we are interested in to establish the relationship between those variables to, run the simple experiments, not just to run like a bunch of hundreds of experiments to find the relationship. So we can just through the dimensional analysis for those variables. Then that was what we got. This one's a pi1, pi2, pi3. So of course, we have a dependent variable d here, drag force. Then that was the pi1. Then in order to design the model that can predict all the drag force and as well as the flow field around the plates here on the prototype, we can have another dimensionless coefficient here, which is d. It's a function of all the variables in the model, which should be, for example, scaling down into like a 1/10, something like that. Then we don't have to consider all the variables one by one. We just focus on the pi terms because we have assumption that my model is pretty much geometrically scaled down, but still has a similar, very similar to the prototype we have. So we can just apply the same function between the pi terms. Then, of course, we can just put the same variables for the model within the pi terms. Of course, the unit is still dimensionless. Then we can just look at each pi term one by one. The first pi term is the width per height. So width per height was the one of the pi term, then it should be the same in the prototype. So that means W over H for the model has to be same as the W over H in the prototype. Sometimes we put like P like that. Then we have another pi term has the same number for the in terms of a pi term. So when you put all the variables in the model, that pi term should have the same value that for the prototype. Then finally, if those are satisfied, those are all satisfied though. Okay, let me just, so when you check these ones, then you can conclude that your prediction equation, which is the dependent pi term, also satisfied for both model and prototype, okay? So basically, in order to conduct these types of dimensional analysis, all three pi terms here has to be satisfied the relationship phi here, okay? So here's a drag force. Finally, we can just set those pi terms same. Then we can finally find the drag force and all the equation here, which is just a scale of the velocity scales of scaling of density scaling of the width here when you measure the drag force in the model. Then you can predict. In the prototype, okay? So to do this similarity analysis, all the corresponding pi term should be the same between the model and the prototype, all right? If it has like a 4 pi term, so you can just compare 4 pi terms between the model and prototype. If it's just a 1 pi term, you can just make this 1 pi term as same as possible. Pretty much close to later, you're not going to see exact same pi terms. You might have a little bit of error between. It's really hard to control all the variables exact in the prototype. But then when you just match the Reynolds number or the one single pi term for the flow field, usually the Reynolds number, then you'll see the dependent variable should be predictable by the experiment. All right, so those are not that, still not intuitive at this point. So let's take a look at one of the example problem in the textbook. So here we are given we have a bridge which is pretty much anchored in the bottom or anchored in somewhere. There's nothing is shown here. Pretty much you can think about the wind tunnel that arm is attached to the side, then hanging on the middle of the wind tunnel. So when you have an elliptical cross-sectional area here, then the vortices shedding is shown after this object. Then we try to scale down in the lab to find the similarity between the model and the prototype before we build the real size of the bridge, right? This vortices or any kind of flow can affects like any, let's say, it's a boat activities in the river or in the ocean, something like that. So here we are interested in to find the HM, which is the height of the model, which is height or width. I think it's a width is more makes sense, but HM and shedding frequency is given for the model. So which is WM. Then we are trying to find M and omega here. So omega is a corresponding frequency for the prototype. Sometimes we call it the omega P. You can just skip the P here. Then those variables are given here in the function. We have a D, H, then the wind velocity, which is a V he's given. And we have the air is in the real system. Then the shedding frequency to be determined through the use of the small scale model, yep, in the water. So that is one prototype in the air, model in the water. So we have two different materials, fluid medium for the lab here. Does it work? Let me see. So models, we have given the D, which is the heights of the breach here. It's given and the water temperature is given. Of course, we need to consider the water to take all the values of the property of the water and the air. Okay, so if I write down the functions, the shedding frequency, which is omega, not W here, is a function of D, H, V, rho, mu. That's all given here, all right? Then the next thing you're going to do is just express these variables in the unit. So we have omega, D, H, V, rho, mu. So let's use the MLT system. I think I need more space here. Then this is T minus 1. This is the unit. This is L. This is also L. This is velocity, density, ml minus 3. The mu, let's just have more space here. L minus 1, T minus 1. Okay, here the frequency is pretty much, this is the same as the hertz. It's a revolution or per second. Let's say this time. Then we have the units of 1/2, right? It's already expressed the every one revolution of the rotation or the interval. So we have just a T minus 1 here. Okay, so can you just find the first pi term here by inspection? Here, you can find them right away, right? Regardless the repeating variables or reference variable, you can just find the one here right away. If we have a K minus R, and so we have a 1, 2, 3, 4, 5, 6. And then MLT, MLT, all three has been used, so 3. You will have a 3 pi terms, but the first pi term is already fine, like a D minus H, right? By inspection. And for example, let's say we pick the repeating variables here. We need to pick 3 of them. So first of all, I'm going to pick D because it represents the one of the L. Then another one represents the T. In the simplest form is going to be V. Then the omega is the one we are trying to find. So it is a dependent variable, cannot be the one. H has the same unit of the length in the D. So we can choose this one too. There's a one choice. There's 2 choices between the rho and mu now. Of course, we always pick rho first since it doesn't have any time unit, but you can choose a mu and manipulate the pi term later, but usually we pick rho here. Okay, so we have done this like at least twice or 3 times. When you pick the repeating variables d, v, rho, and mu, we have a pi term, the second one. So Reynolds number, rho v d over mu, right? So later, once you just see the list of the variable, you just come up with the Reynolds number right away. Because we know if I pick like d, v, rho, and it's going to be combined with the mu, then we're going to always have the pi term, the Reynolds number, rho v d over mu. So the third one, the pi 3, the third pi is going to be, you can just find it. The omega is the one dependent variable, so we have d, v, rho, then put the exponents a, b, c, and just one dot. Then we can just put all the dimensions here, L, LT minus 1, rho m, L minus 3 equals MLT 0, 0, 0. You have A, B, C. So when you solve it, first thing T is the easy one, minus 1, minus B equals 0. The B is minus 1. Then there's L3M. So we have just one M, which is a C, should be 0. So, okay, easy. Then L, we have A plus B should be 0. So A is 1. Okay, so the last one is now we have omega. A is for D. And there's a no density. We just have a velocity. So this is the third one. So we have 3 pi terms. Then for the relationship between the model and the prototype, we can just consider the similarity among these 3 pi's. Then you can just find whatever the variables we want to predict in the prototype. Okay? So if I write down it's pi 3 is going to be some function of pi 1 and pi 2. Okay. Once I export my PDF in the OneNotes, it's a little different than I importing the PDF, I guess. All right, I need more space. Let me just make here. All right. Let's just use this space, and I'll just make the notes more clearly there. Okay, let's just use the space here. All right, so now it's between the model and the prototype. We're trying to find the HM. So the omega m is given. It's a 49.9 hertz. Then we can just list all the variables we know of here. So first we have D is a 0.1 meter, and D model is a 0.02 meter, which is given as a 20 millimeter. So I just convert it into the meter. The H is a point that's given here, 0.3 meter. HM is still don't know. We're gonna find it. Then what you have is a velocity. So 50 kilometer per hour. So if you just convert it into the meter per second, you'll find the 13.9 meter per second. So what we're going to, the next step is just simply apply all the similarity based on the pi terms. First, pi term here is going to be d over h of the model has to be same for the prototype. Simply set it like that. What you have here is 0.1 over 0.3 for the actual device. So let's just solve it like this here. 0 over 0.3. So when you're looking for DHM, is going to be dm 0.3 over 0.1. Then dm is given 0.02, so we can just find it's a 0.06 meter, same as 60 millimeter. Okay. So this was the geometric similarity. We can just simply find the geometric similarity from the first pi term. And the second pi term, so rho VD over mu, Reynolds number of the model has to be the same for the prototype here. You can use the subscript P here. All right, so in order to make this similarity satisfied for the pi 2, we have to find all the characteristics of the fluid. So first model is for the water. And at the temperature is 20 degrees Celsius. If you look up the table, the probability table 1.6 and 7, I guess, you'll find the viscosity 0.001 kilogram per meter second. Density is pretty much close to 1,000. Exact numbers are 998 kilogram per meter cubed. Then for the air, it says air in the standard, where is it stated here? Yeah, standard air condition. So you can just look up the table again. This one gives you the number. Let's just make the subscript here. Find the values from the table. It's still kind of weird because we are trying to predict the flow field behavior in the air by water. Okay, so when you have a mu and rho, you can just plug the numbers here, right? Let me just check it. Here's a rho is given, mu is given, rho is given, mu is given, and d and dm is also given here and there. And what you have, the velocity in the prototype has given, so which is this one is given. So you can reorganize the equation in terms of the other variables for the velocity in the model. When you do it, the Vm is a rho over rho m, mu m over mu, d over dm. Okay, so when you scale down the prototype into the model by here, like a scaling, geometric scaling, it's about like 1/3, not 1/3, 0.02, 0.1. So it's going to be about like a, how much is it? Like 2.2 is a 5. So scaling is about like a 5, but you can just justify the velocity is going to be 1/5 of the prototype. No, it's all about the materials and all about the geometric scaling in the model too. So when you just plug all the numbers you have here, the velocity is going to be 4.79. Then once you have the velocity, you can now get into the pi 3, the third pi. Just erase it. Then plug the numbers now. So it is omega d over v for the model has to be the same for the prototype. Then you have a v here. You have a v here is given. D is given. dm is given. The omega in the model, the omega m is given. So we can just find the predicted results for the prototype can be calculated. So omega is going to be dm over d. The v1, no, just v over vm. Then omega m. So you can figure out it's 29 hertz. All right. Why they use the water instead of the air here? If you use the air, the Vm, of course, the equation is the same because of the similarity. We just scale down and just keep the same fluid within the model, dm. Then it's going to be, you will find a 5v, which is 5 times higher in the model. Okay. So it's going to be about like a 69.5 meter per second. It's about, and it's just much higher, right? Even if you scale down, sometimes the velocity is increased significantly in the model. So which actually the purpose of the lab and model is we just trying to simplify the model to make the measurement easier. But if the velocity is much higher than we expected, we have to use like a fancy dock board, fancy equipment to measure the millisecond or the microsecond scale. And we have to measure something really fine resolution, using the fine resolution to find all the differences within the system in the model. So that's not we want to do it. Therefore, we just change the material, change the medium of the fluid to match the pi terms between the model and prototype, then just keep everything else just within a reasonable range in terms of pi terms, which is a dimensionless number, all right? So for example, if I calculate that with the air, then you're gonna end up have the omega model is going to be about like a 725 hertz. So previously, the frequency of model was a 49.9 hertz. So it's about the 50 hertz. It's just a little less than the 60 hertz we have in the outlet, so which is really the lower number. You can use a really cheap analog digital converter device to get the sampling to those accurate result out of it. But this is also like more than 10 times than the one we used to have. So it's always to find the optimal range of the modeling conditions. Something like scaling is one of the biggest one. You want to just minimize it, but also all the variables in the system, like velocity, should not be exceed reasonable range. Something like you don't want to measure like 100 meter per second speed within the model in the small scale, in that tabletop, right? That's one of the criteria when you design the model and the experiments. All right, let me just pick up the other some practical models in the chapter 7.9, and hopefully I can just finish up the chapter 7 tomorrow. Then I'm going to just also talk about the exam for next week. All right. Okay, so lab